cart, a ramp, a ruler, a stopwatch. Let us think upon research upon the bare minimum. Following the principles that we take before on the other class. The quality of the experiment does not depend on the expensive equipment. It depends on the care we take when asking a question, controlling, measure, and measuring. If, for example, if I release this car twice, what does it look like at the same place? It travels times exactly identical. Of course, that is when you have some variations. Measurements are rarely perfect identical. There are very few cases. Light is one of them. Light is always the same to every observer. Basically, a principle that modern physics stand upon. So even if you don't get exactly the same results, for example, when you're trying to measure light, you will run across problems with measurement because simply the equipment is limited. The measurement does not mean that it failed because you didn't get light identical as C. We don't have exactly the top-end research equipment that worldwide. One second. I told him not to. Okay. So our job is to consistently use the method, repeat the measurement, and decide wherever a pattern is larger than the ordinary variation of our results. Second. Okay. How do we know a change really caused an effect? Basically, a standard on physics is cause and effect, A and B. You have A, an initial state, and you have B, the final state. Usually, all logic works upon this core idea that you have a situation A that will lead to a situation B. And suppose we raise the ramp, the cart reaches the line sooner. You have A, we make an action. We raise up the ramp. B, the cart gets faster. But is that the best B that you can describe upon? You raise the ramp A. Does the cart getting faster is the best B that you can say to that kind of A? That is a research problem. Basically, what is the action A? The best is B, energy increases, for example. And you get better and better Bs and better. One second. We're back. So, to change the height of the ramp, but also use a different cart. Push it harder, move the finish line. All those are A's. And you have different B's. But the complicated is because you can only get a B on a very instant to verify, but you can't know the exact A's of your sample size. Because when you, for example, A, get the higher cart on a higher elevation, okay? How do you know you didn't move the ramp? A bit to the left, a bit to the right, or some change upon friction on the wheels that may change the result and is not related to A, increasing the ramp height. All those questions you need to verify with the cause and effect in a way that will be better to analyze. You can get the B of an example and use it as an A. For example, A, we raise the ramp. B, energy increases. Use that as an A. A, energy increases. Therefore, potential increases. B, potential increases. B, A. Therefore, energy difference increases. B, A. Energy differential increases. A, and B, equalization becomes harder. For example, let me just check if you guys have any question, because I'm sharing the screen, but it's not very ergonomic for me to check because it's transmitting the whole screen. Okay. So with that, we need to basically use a lot of tries to get the most of an experiment. 1 second. What can actually be tested in that manner on putting A's and B's? What defines, measure, and fix states? What compares and isolates the cause? What measure, number, and instrument? Repeat, variations and anomalies, and plan. Think upon what a group can do in the measure of doing research on cars and ramps. What questions can they make? What things can they test? What is the sequence that they will follow? Mainly, it starts by first asking a focus question, next defining what changes and what is measured, and what stays fixed. We compare fairly and measure unit with instrument, and repeat enough times to see the variation. That is the gist of it. Only after that we write a plan and later a conclusion. We do not choose the conclusion first and then search for numbers to support it. The method and evidence must guide you to what we say. We must first ask a question and then answer, not having an answer and make the experiment basically confirming that is confirmation bias. You usually want to avoid that at all costs because it make that is the base of religion, not science. When you have an answer and you want to question things, not question. The problem is that you have something, a narrative. You want to confirm that narrative, then you make the experiment to go, hey, see, that's what I said. That is usually not how things go. We have questions and the answers comes after the questions. We're not going to B and A in the wrong order. We must see the A and then the cause and then B the effect. Any questions as far? But the quality of the lecture is good today. It's better than the other days. I wanted to make it more complicated, but I had time to do the script, but I think I will be able to pass an idea that will be solid for the next week. A fair test changes one thing at a time. Scenario: we want to test whether the ramp raises height changes the travel time. Both groups collect data, but only one isolates the probable cause. A confounded test changes multiple A's to check one B. And this way, the contribution that the A's do on the B's is not known. You cannot know if changing the height and the surface of the car will have the same contribution. In the perfect world, it wouldn't be 50-50. You change things equally, but on science and on the day-to-day, we don't have that. So both groups want to test whether the ramp height changes the travel time of the car. In the test on the left, let's imagine the group changes the height and the surface using different cars to run one and only trial. Even if the time differs, we'll not know what changes mattered. We don't know if the surface itself changes the time more or the height had a bigger contribution. On a fair test, we change things one at a time, 1A to 1B. We do cows, we change one thing and the most isolated and the most subtle way possible to the bigger B to calculate it. The test on the right, let's think, left and right, changes only the height and then measures faster speed. Then you go to original height, change the surface, check if we got faster, see the contribution, and so on, doing tests and tests. Several tests and possible causes is called no, I mixed it up. A test with several possible A's to one B is called confounded. The number may be real, but the explanation is weak because the number of causes are mixed together. The independent variable. Every investigation separates three rules: independent, what do we see or change and purpose, range height; dependent, what we measure, and controls. The independent variable is what we intentionally changing. In our example, the ramp height is measured in centimeters. The dependent variable is on the response, is the B. When we measure, is the travel time measured in seconds. Control variables are important conditions. We replicate the same: the car, the ramp surface, path, length, the release point of each condition, the release method, the finish line, and timing rule. That are the invariables. Basically, we don't change that. We keep as stochastic. So we change a thing, change a B. Think as a medium when the experiment run, the uncontrollable parts of the experiment. Second. You can join the other space if you wanted. If this takes too long, you can join the other one. I will try to be quick. The lesson is simple. Be mindful of the measurement. The things itself, the detection change the result. So you must be mindful of the assumptions one make, the questions, and the control environment we use. a strong question already suggests an experiment. A strong investigative question tells us what will change and what will be measured, and what enough about the system to guide a fair test. We can use this structure to how x affect I and z stays constant. For our investigation, how does the ramp height affect the travel time in the same cart over the same path? Comparing that, what makes a car fast? What the question is interesting but is too broad for one investigation. Is tying upon the what is that making the cart go higher has to do anything with speed. Do you see that? You can see the ties to energy. It already putting upon what is the effect B that describes well the system. Spoilers is the difference of energy. With measurement follow a protocol. Before, prepare, choose an instrument, a unit, a release point, during, repeat. This is important. The more times you repeat an experiment, the better. Of course, inside the practical limit, you're gonna not run a billion times, but I've seen professors toss a coin more times than I can remember. I think it was 200 times. 200 times, no, it was 20 or 100 times. 100,000 times. It was a lot. Experiments that had quality have repetition. They have lots and lots of repetition. And the recording, writing everything down, every anomaly, every point, not discarding anything. Example. A good chart is it starts simple like that. I will finish here to allow people to go to the aerospace one, so it's better. I also want to watch it. Thanks for having me, and that is all. Sorry if the class is too short or too light on content. Alpha, do you want to take it from here? Alpha? CJ?
Was refreshing.
Come again? Whale, do you want to say something? Yes. I am able, but yes. Your audio is cutting.
Yeah, you're breaking up.
So, while CJ fix the issue, do you want to say something, Will? Professor Will Whisper?
I was saying that your presentation was refreshing.
Oh,
I was
thank
thinking
you.
I was thinking the whole time of how I might ask the right question that would have a difficult answer. A what if question,
Yes.
which you covered it pretty well.
Thank you. Okay, but that is it for the lecture. I thought we hadn't too much time, so I made a shorter one.